Sponsored by Maddox. This is a three-phase transformer. It has a delta primary and a Y secondary and is rated for 2 kVA. Confused? Well, don't worry, I will explain all of that. The transformer basically just takes an AC voltage and converts it into another voltage. We can get 1, 2, or even 3 different voltages out of the secondary side, but there are no moving parts inside and there are no wires connecting from one side to the other. You've likely seen these big green boxes at the side of the road. Inside is a three-phase transformer. These supply power to commercial buildings because they have a lot of lighting and equipment inside. Your home has much less stuff, so you only get a single-phase transformer. This might be pole-mounted or pad-mounted. We can see there are 3 wires going to the home, but this is not a three-phase transformer. They typically connect to just a single phase and the neutral of the distribution grid. It then reduces this voltage to a much safer level. Inside, we basically have a primary coil which connects across the phase and the neutral. Then we have another completely separate coil called a secondary, and the 2 hot wires connect to the ends of this coil and the neutral connects to the center. These wires run into the property to your electrical panel. The primary side has a single-phase AC supply. The secondary side is also a single phase between the 2 hot wires, giving us 240 volts. The current and voltage are flowing forwards and backwards between these two as it is alternating current. But if we connect from the neutral to one of the hot bus bars, we get 120 volts because we're using just half of the secondary coil. The other side is also providing 120 volts, and it uses the other half of the coil. If we plug an oscilloscope into the outlet, we would see a sine wave. This sine wave has a positive and negative half of the AC sine wave. If we connect to each bus bar and the neutral, we see one side is positive 120 volts, while the other side is negative 120 volts. The difference between these gives us 240 volts. So this is just a single phase that is split into 2. However, you'll often see banks of 2 or 3 transformers which do provide 3-phase power to commercial buildings. But where did the 3 phases even come from? Well, the power station generates 3-phase AC electricity. The generator basically just spins a magnet past a coil of wire. The magnetic field pushes and pulls the electrons in the coil forwards and backwards as the strongest part of the north and south pole passes through the coil. This creates the sine wave with a positive half and a negative half, and this is a single phase. The generator spins the magnet fast enough that the sine wave repeats 60 times per second, and that gives us 60 Hz frequency. But notice the output power is not constant with single phase. We could add another coil which adds another phase and helps to improve this. Or we can add a third coil giving us 3 phases, and we see a much better constant output power. Notice we have 3 phases but 6 wires. Also notice the current is always flowing forwards in one coil and backwards in another. So we can combine the coils and the current will share the wires, only using them when they need to. We could try sending this power directly to the property, but it's very far away. So the resistance of the wire means we will lose a lot of power just trying to get it there. However, if we increase the voltage, we can send the same amount of power with less current. So we lose almost nothing. The power station feeds into a step-up transformer. This increases the voltage to hundreds of thousands of volts, and this will keep the current low over the long distance. Then, when it reaches the city, it enters a substation, and the voltage is reduced in a step-down transformer. This continues on the sub-transmission lines, and it might feed some larger industrial or commercial sites with their own dedicated substations. But it otherwise continues to the distribution substation, where the voltage is again reduced and then distributed out along the streets to the properties. Homes will then connect to one of the phases, while commercial properties will connect to all 3 phases. Now, if you need to buy a transformer, keep Maddox in mind. They're basically like a transformer superstore. They have transformers of all sizes in stock and ready to ship all across the US from 15 kVA up to 15 MVA. They have both dry type and oil filled. If you need a transformer quick, call Maddox Transformer. You can also check out their channel for some great tips and tutorials too. I'll leave a link for you down below. Do check them out. Three-phase transformers come in many designs, but inside we basically just have three single-phase transformers joined together. A transformer is simply two separate coils of wire placed around a steel core. When current flows through a wire, it produces an electromagnetic field around the wire. When the current changes direction, the magnetic field also changes direction. When we wrap the wire into a coil, the magnetic field joins together and forms a larger, stronger magnetic field. When AC current passes through the coil, the magnetic field will increase and decrease as well as change polarity as the current alternates direction. If we place another coil in close proximity, the magnetic field will interact with the electrons in the second coil, and the magnetic field induces a voltage into that coil. If the path is complete on the secondary side, then a current will also flow. However, a lot of the magnetic field is currently being wasted, so we use a steel core to concentrate and direct the magnetic field, making it stronger and more efficient. The magnetic field will move around the core. This will induce an eddy current within the core material. This wastes energy and it also generates heat, and we don't want that. So we use lots of thin laminated steel sheets to build the core. This helps keep the eddy currents as small as possible. So when we apply a voltage to the primary side, we get a voltage on the secondary output side, and the frequency will remain the same. If both coils have the same number of turns, then the output voltage and current is the same as the input voltage. If the secondary side has fewer turns than the primary, we get a lower output voltage but a higher current, and this is a step-down transformer. If the secondary side has more turns than the primary, then we get a higher output voltage but a lower current, and this is a step-up transformer. In each case, the power transferred is the same value. For example, if this step-down transformer was supplying 200 volts and 10 amps to the load, then we have 2000 volt amperes on the secondary side. The primary side would see 5 amps and 400 volts, which is also 2000 volt amperes or 2 kVA. So the power transferred is the same, but the voltage and current change. Now, we could have 3 separate transformers, but to save cost, material, and space, we often combine them. The 3 coils on the primary are connected to the phases in either Delta or Y configuration. The secondary side coils can also be Delta or Y. So we can have a Delta-Delta, a Wye-Wye, a Y-Delta, or a Delta-Wye transformer. The nameplate on the side of the transformer will tell you how it's configured. For Y configurations, we connect one end of each coil together. The other end connects to a phase. Notice it looks like the letter Y, so it's easy to remember. From the central point of the coils, we can connect a neutral wire and also a ground connection. This allows us to connect to a single phase or all 3 phases. We can see with this transformer that one side of each coil connects to a dedicated terminal for each phase, but the other end of each coil connects into the same point using 4 terminals. So we know this is a Y connection. With the Delta, all the coils are connected end to end, with the phases connecting between the coils. This forms a triangle that looks like the Greek symbol for delta. There isn't a neutral with this design, so it's only for 3-phase loads. However, there are some variations like the high leg and the open delta, but I'll explain those later in the video. With this transformer, we can see each coil connects to a terminal, but the other end of each coil connects to a different terminal, so we know that this is a delta connection. The coils could be on either side of the core, but we usually find them placed concentrically with one surrounding the other. So maybe we have a pad-mounted transformer powering a small commercial building. The stickers and nameplate tell us it's a 12,470 volt Delta primary and a 208 120 volt Y secondary, and the transformer is rated for 150 kVA. So we have 3 phases and 3 wires entering the transformer's primary side with 12,470 volts between each phase. The secondary side is Y connected with 4 wires leaving the transformer. It's a step-down transformer with 208 volts between any 2 phases or 120 volts between any phase and the neutral. It can handle up to 150,000 volt amperes in total, so that's 50,000 per phase or per coil set, which means we can supply up to 416 amps on each phase and through each coil on the secondary. And that would cause 4 amps to flow through the primary coils, and that causes 6.9 amps to flow through each line. That is our maximum limit for the transformer. The actual kVA transferred depends on how much equipment you connect and power. We just can't exceed the transformer's limit, otherwise it will overheat, cause a short circuit, and it will simply burn out. Our next example is this larger commercial building, which might need to power 480 volt 3-phase motors, 277 volt fluorescent lighting, 208 volt appliances, and 120 volt outlets. Outside the building, we find a pad-mounted transformer rated 12,470G/7200, and that's on the primary side. And on the secondary side, we have 480 volts/277 volts, and the transformer is rated for 500 kVA, and this is supplying the building. We know it's a Wye-Wye transformer with 4 wires entering the primary side and 4 wires leaving and entering the building. It also tells us that the primary side is grounded. So there's 12,470 volts from line to line, or 7,200 volts from line to neutral on the primary side. And there's 480 volts line to line, or 277 volts line to neutral on the secondary side. Now, this might enter the building and connect into a switchboard, and from here it might feed a panel which feeds a motor 480 volt 3-phase. And maybe it feeds a panel which supplies a smaller step-down dry type transformer, and that transformer feeds a 208/120 volt panel. This smaller transformer is 480 volt Delta primary and 208 volt 120 volt Y secondary, and the transformer is rated for, say, 30 kVA. So this provides 208 volt 3-phase or 120 volt phase to neutral. Inside this transformer, we have 3 coils, and the terminals labeled H1, H2, and H3. This is our high voltage side, where the phases connect for the delta connection. Then we have X1, X2, and X3 along the bottom. This provides our 3 output phases, and there is also an X0 terminal for the neutral. Notice on the coil these black jump leads and the 7 connection points on each phase. These are called taps. We can move the jump leads to increase or decrease the length of the coil. Let's say we have 84 turns on the primary with 5 taps and 20 turns on the secondary. We measure the supply side and have 480 volts. So the data sheet says to use tap 3 on all phase coils. This has 80 turns and provides the designed 120 volt output. However, if we measured 504 volts on the supply side, we would get 126 volts on the secondary. So we need to increase the coil, and we use tap 1 with 84 turns to reduce the output voltage back to 120 volts. But if we had only 456 volts on the primary, then we'd need to use tap 5 with 76 turns to get the 120 volt output. So we can compensate for supply voltage variations using these taps. We usually find the primary coil on the outside because we can easily change the connections. The large pad-mounted transformers also have tap changers, but the coils are submerged in oil for cooling, so we can't access them. The coils therefore connect to different points of the tap changer, and the dial changes which parts of the coil are connected across. We often find smaller commercial buildings supplied by 3 pole-mounted transformers connected in Delta-Wye. This provides 3-phase 208 volts or single-phase 120 volts, or it could be 480 volts and 277 volts. Sometimes they are connected delta-delta, usually providing 480 volt 3-phase only. Sometimes only 2 transformers are used, forming an open delta. It typically provides 240 volt 3-phase and 120 volt single-phase, with a high leg of 208 volts. However, this design is missing a coil, so it has a reduced capacity. I'll explain why in just a moment. I've made these 3-phase transformer mugs with the formulas and diagrams on to make it very easy to remember. And you can grab my PDF sheets too. Links down below for that if you'd like one. For Y connections, we have all 3 coils joined at the center. At this point, we normally ground the transformer and we run a neutral wire from here. So we have a 3-phase 4-wire system. This gives us our line voltage or line-to-line voltage, and also our phase voltage, which is often called the line-to-neutral voltage. In this example, we have a 208 120 volt secondary, so we have 208 volts between any 2 lines, or we have 120 volts between any line and the neutral. Now, it's the coil that's producing the 120 volts, and that just depends on how many turns the coil has and the primary applied voltage. The simple reason we get 208 volts is because we are connecting across 2 coils, but these coils are not in phase. One is in the positive while the other is in the negative cycle. At the widest point, roughly 120 degrees rotation, phase A will be 104 volt RMS, while phase C will be negative 104 volt RMS. So the difference is 208 volts. Or we can solve using trigonometry. We have 3 coils which are all 120 volts, and they are 120 degrees rotation apart. So all we need to know is the length of the side of the triangle. From trigonometry, we use this formula and drop in our values, and that gives us 208 volts between 2 phases. Now, no one wants to write that out every time, but notice the ratio between the 2 voltages. It's around 1.732, etc., etc., etc. This number just goes on and on. So engineers just say 1.732, or they use the square root of 3 because it's even easier. We get that because if we square this ratio, meaning we just multiply it by itself, then we get 3. So to undo that, to find the original or the root number that was used to make this square number, we just take the square root. So the square root of 3 is 1.732, etc. Therefore, if we know the phase voltage, we multiply this by the square root of 3 to find the line voltage. And if we know the line voltage, then we divide that by the square root of 3 to find the phase voltage. Luckily, the current in the Y configuration is super easy. The phase current is the same as the line current. So if we had 100 amps on the line, we would also read 100 amps through the coil. In the delta connection, each coil is joined end to end. The phase wires connect to the intersections between 2 coils. This gives us a 3-phase, 3-wire system. There is no neutral, so we only have line voltages. In this example, we have 480 volts between any 2 phases. The line voltage is the same as the voltage across the coil, or the phase voltage, because we only have 1 coil between any 2 phases. But the current is split between 2 coils, and we know that they are flowing at different times. So the line current will be larger than the phase current. If we know there's 43.3 amps flowing on the line, then we divide this by the square root of 3 to get 25 amps on the coil. And if we know the coil current is 25 amps, then we multiply by the square root of 3 to get 43.3 amps on the line. A fairly quick way to mathematically see that is to simply draw each of our coil currents 120 degrees apart. To find line A current, we have coil C to A and coil A to B connected to it. So we reverse coil C to A, which would sit 60 degrees apart from the other two coil currents. Then we slide that line to the end of the AB coil current line, and really we're just making a parallelogram, but we're going to skip that step. We know that this angle must be 180 degrees total. So 180 degrees minus the 60 degrees we already have means this remaining angle is 120 degrees. So our line current will be the resultant line between these 2 points. So now we just have a triangle with an unknown side, and we can use trigonometry to solve that. So our line current is therefore 43.3 amps, which is 1.732 times larger than the coil current, which is equivalent to the square root of 3. So if we had a Delta-Wye transformer with 80 turns on the primary and 20 on the secondary, we have a ratio of 4:1. The primary side has 480 volts between 2 phases, so there's 480 volts on the coil. We calculate the voltage in our secondary coil as therefore 120 volts, and that is our phase voltage. So we can then easily find the line voltage of 208 volts. The secondary side has 100 amps on each phase. We find the primary winding current of 25 amps through each coil. The current on each line is therefore 43.3 amps. So the primary side power is 36,000 volt amperes. The secondary side is also 36,000 amperes. So the power transferred is the same, but the voltage and current are transformed. In the high leg delta, we have 3 coils connected in delta. In this case, the voltage between any 2 phases is 240 volts. The voltage across the coil is also 240 volts. But one of the coils has a wire connected to the center of the coil. This is also grounded. The wire acts as a neutral, so we can use half of the 240 volt coil to get 120 volts between phase A and neutral, or between phase C and neutral. However, between phase B and neutral, we get 208 volts because we are using 1.5 coils. We can find that using trigonometry. This is why the B phase will usually be orange in the panel to warn it's a higher voltage. And that's because it will likely destroy any 120 volt appliance if it's improperly connected. The open delta uses just 2 transformer coils, so it's missing one of the coils. We get the same voltage in the coil, so it's the same voltage between lines and the same voltage between the line and the neutral. However, the capacity is reduced. If we had 3 transformers, each rated 20 kVA, that gives us 60 kVA in total. Then the maximum coil current or phase current would be 83.33 amps, and the line current is therefore 144.33 amps. But with only 2 coils, the maximum line current is equal to the maximum phase current. So our total capacity is now just 34.6 kVA. That's 57.7% in comparison, or a reduction of 42.3% compared to the 3 transformer delta. Our rated capacity for this 2 transformer design is now just 40 kVA, but we can only handle 34.6 kVA, meaning we can only use 86.6% of the stated capacity. So this design is cheaper to install, but it's not always practical. However, it is easy to increase at a later date. Hey, I'd just like to give a huge shout out to our incredible Patreon and channel members. Thank you so much for supporting us. And if you'd like to see your name here, along with priority access to our content and behind the scenes footage, links down below for how to join.